Okay, welcome to our first face-to-face meeting of the semester for Stat 151. I'm going to discuss some questions from section 1.1. Before I do that, I just want to start with a couple of sort of hints, things to remember when you're working with the material in this section. The first thing I want to just mention is that when we're finding the probability of A intersect B, some of you may have taken other courses in the past where you've found intersections by multiplying probabilities. We have not talked about multiplying probabilities at this point in the course. We're going to do that in Module 4. So at this point, we have two ways that we can try to find the probability of an intersection. The first way is that we know that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. So we could rearrange this equation, use our algebra, and find the probability of A intersect B as the probability of A plus the probability of B minus the probability of A union B. So that's one approach we could use so far. The other approach that we have, if we have a sample space in which all of the outcomes are equally likely, then we can use what we call classical probability. We can find the probability of A intersect B by counting how many outcomes are in the intersection of A intersect B. And we denote that with this N. A intersect B means the number of outcomes in the intersection, and divide by the total number of outcomes in the sample space S. So those are really the only two ways we have so far to calculate probabilities of intersections. If we try to start using multiplication rules, a lot of times we misuse them right now because it's a little more complicated than sometimes people recall from thinking back to their intro stats courses. So for now, work with these methods of finding probabilities of intersections until we get to Module 4. The other thing I wanted to mention is just that one thing that is extremely useful for finding probabilities is De Morgan's law. Anytime that I see a situation where I'm looking for the probability of A complement union B complement, or the probability of A complement intersect B complement. When I see two complements in here, often it's easier to work with De Morgan's law, which tells us that A complement union B complement is equal to A intersect B complement. So what this means is that the probability of A complement union B complement is equal to 1 minus, so this is the complement of A union B, the probability of A intersect B. And similarly, if I'm trying to find the probability of the intersection, De Morgan's law tells me that A complement intersect B complement is equal to A union B complement, so the complement of A union B. So when I want to find the probability of this intersection of A complement and B complement, it's often easier to find 1 minus the probability of A union B. So just something to keep in mind sort of as you're looking through, if you're thinking in terms of when I see complements in both events, often it's easier to kind of switch it around and use De Morgan's law. So those are just a couple of sort of general comments. Okay. More specifically now I'm going to go to some of the things that people had questions about on the discussion board, which was mostly the homework questions. Let's see. So this is question 1.1-4. This is the one where a fair coin is tossed 4 times and the sequence of heads and tails is observed. The first part of it was to list the 16 outcomes in the sample space. And just as a reminder, when we list the outcomes in the sample space, sample space is a set, so we should be using set notation. So here are the 16 outcomes, ordered sequences of heads and tails. Now, because we have equally likely outcomes, the way we're going to assign probabilities is by counting how many outcomes are in each event that we are trying to calculate the probability of. So the probability of event E is going to be the number of outcomes in event E divided by the number of outcomes in the sample space. So the way to sort of get started with this really is to start thinking about, we have A is having at least 3 heads. So first thing to do is look through and say, okay, well, which of these include at least 3 heads? So I've got heads, 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 heads. I've got heads, 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 tails. I've got heads, heads, tail, heads. I've got heads, tails, heads, heads. And I've got tails, heads, heads, heads. And those are the outcomes in event A, which again is a set. Now B is the event that I have at most 2 heads. Notice that having at least 3 heads and having at most 2 heads, those are complements of each other, right? If I don't have at least 3 heads, that means I have at most 2 heads. So I'm going to be choosing all of the outcomes that are not in A for B. So I'd have heads, heads, tails, tails, heads, tails, head, tails, heads, tails, tails, heads, tails, 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 heads, tails, tails, heads, tails, tails, heads, tails, tails, heads, tails, 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 heads, heads, tails, heads, tails, heads, and then tails, heads, heads, tails. So all of those outcomes would be the event B of getting at most 2 heads. And I could do the same to list all the outcomes in the other 2 events that are described. I'm not going to go through and do them all, but just to sort of give us a sense of where we're going. So now if I want to figure out the probability of an event, again, the probability of A, I'm going to figure out the number of outcomes in A and divide it by the number of outcomes in the sample space. We know there are 16 outcomes in the sample space. And in A, I have 1, 2, 3, 4, 5. So my answer should be 5/16. If I'm trying to find the probability of A intersect B, I'm going to look for what the intersection is between A and B. Now, we already said that they're complements, so what's in A is not in B. So the intersection of these 2 is null set, empty set. There's no intersection. So when I look at the number of outcomes in A intersect B, divided by the number in the sample space, this is going to give me my probability of A intersect B. There are no outcomes here, so I have 0 divided by 16. So the probability of A intersect B must be 0. So, and so on. So the same idea can be applied. The key is to figuring out exactly which outcomes are in the union or the intersection that you're interested in, or the complement that you're interested in, and counting them and then dividing by the total number of outcomes in the sample space. Okay. So I'll let you keep working through that for people who are still finishing that one off. Let's see. 1.1-6, there was a question about part C. And this one, like I say, this is one of those situations where I say, I see the two complements here. I'm going to say, okay, when I have the two complements, I'm looking for a union of two complements. Right away I'm thinking it might be easier to work with De Morgan's law. So I'm going to use the fact that A complement union B complement is equal to A intersect B complement. So I'm going to try to see if I can figure out, which means that the probability of A complement union B complement is equal to 1 minus the probability of A intersect B. And that's going to help me solve my problem. Because now all I need is A intersect B, probability of A intersect B. Any questions from the people here so far? Okay. 1.1-12 is a little bit different from the other questions because all of the other questions we have countable number of outcomes in the sample space. In this problem, we're saying our sample space is a continuous interval from 0 to 1, right? So we can't think about counting outcomes because we have an uncountable number of outcomes in any interval, even in any subinterval of this. We have an uncountable number of outcomes. So this was really asking us to just instinctively try to answer these questions. I think most people sort of start by saying, okay, well, I've got this interval from 0 to 1. And a number is being randomly selected, so that should mean that all of the numbers along here are equally likely to occur. So when we say, okay, well, the first part A asks, what's the chance that the value will be between 0 and 1/3? And I think that most people say, okay, well, this is 1/3 of the total length of this sample space, right? And if all of this entire length of the sample space is equally likely, that means the chance of landing in here should be about 1/3. Okay? So this is something that we're going to discuss more as we get into chapter 3 of the textbook. It's going to talk about continuous random variables. When we have a random variable that can take on an uncountable number of possible outcomes, that's a continuous random variable. And that's something we're going to talk about in more depth and sort of less just based on intuition when we get there. But this question, the book really likes to just sort of introduce the idea that it is possible to have outcomes, sort of a continuous set of outcomes as opposed to countable number of outcomes. So the question, the first couple of parts of this question, usually people have a fairly reasonable time trying to sort of answer on intuition. What gets trickier is when we get to part C, it asks the probability that we have exactly, x is equal to exactly 1/3. In this case, if we try to think about it intuitively, we say, okay, well, what proportion of this interval is at exactly 1/3? What's the length of the interval from 1/3 to 1/3? There is no length to that interval, right? So using the same idea that we were before, we'd say, okay, well, the probability of x being equal to exactly 1/3 should be 0 based on that intuition. But then often people say, well, wait a minute, but probability of 0 means it can't happen. Right? That's not actually true. So that's the first thing, is just because it is, in the case when we have a continuous variable like this, continuous set of possible outcomes, any individual outcome, exact outcome, has a probability of 0, even though it could occur. Okay, so I think sometimes when we work with only countable outcomes, we oversimplify by saying probability of 0 means something can never happen. That's not actually true. So again, this is something we'll come back to in chapter 3 in a lot more depth, but just to sort of give us a little preview, probability 0, when we have an uncountable number of possible outcomes, any individual value has a probability of 0 of occurring, even though it could happen. And as one of our students pointed out, even if I picked out a collection of exact points, if I said, what's the probability that it's 1/3 or 1/2 or 2/3, the probability of each of these is 0, and the probability that it will be one of these particular values is also 0. Very kind of interesting. So as I say, something we'll come back to just to give some understanding, because it is a little strange to think about that one. And then the last part of this question asks about the chance that the value will be between 1/2 and 5. We know that the value has to fall between 0 and 1. So there's no probability associated with anything out beyond 1. So you can kind of think about this, breaking this up and say, okay, what's the probability that x is going to be between 1/2 and 1? And we'll add to that the probability that it will be between 1 and 5, right? So the chance that it'll be between 1/2 and 5 should be the same as the chance it's in here plus the chance it's out here. We know this probability is 0. There's no chance that it's between 1 and 5. So really we just want to think, okay, what's the chance we're going to get a value between 1/2 and 1? And again, we can go back to our intuition about what proportion of the sample space is between 1/2 and 1 to answer that question. So this question definitely is a little bit more of a sort of think it through kind of question, as opposed to doing lots of calculations, but I think a good way to sort of get started thinking about some of these ideas. And then the last of the homework questions, 1.1-16. This is another one where, so P sub n for n is 0, 1, 2, up through infinity, is the probability that an automobile policyholder will file for n claims in a 5-year period. The actuary involved makes the assumption that P sub n plus 1 is equal to 1/4 of P sub n, and we want to know the probability that the holder will file 2 or more claims during this period. So whenever we see something like 2 or more, and we have values of if we think of, say, X is our number of claims filed, X could be anything from 0 up through infinity here. Whenever we see something where we have sort of a really large number of possible claims and we're seeing the chance of 2 or more, it's usually best to start thinking about using the complement to find those probabilities. Right? It's really hard to say, okay, even once I figure out what P sub n is for all the different values of n, I would still have to try to maybe take some sort of infinite sum if I wanted to look 2 or more. It's much easier to figure out the probability of less than 2, right? Which is the complement of 2 or more, and then subtract from 1. So the probability of 2 or more is going to be equal to 1 minus the probability of less than 2. So the tricky part in terms of doing the calculations is figuring out what the piece of n's are. What I advise you to think about is that all of the probabilities are going to need to sum to 1. Right? Then we can write these probabilities in terms of p sub 0, first probability of 0 claims. K equals 0. Okay, so p sub n can be written, if we think about it, our first value is p sub 0. Our second value is going to be p sub 0 times 1/4. Our next value is going to be 1/4 of this one. That's going to be p sub 0 times 1/4 times 1/4. So our value here is going to be p sub 0 times p sub 0, p sub 0 times 1/4 to the kth power. Okay. You can imagine I can keep going with this. And I'd have p sub 0 times 1/4 times 1/4 times 1/4 as my next value, and so on. So this, if we recognize it as a geometric series, since this sum has to equal 1, you can figure out what this is going to converge to, and then solve for p sub 0, essentially. So just a little bit of working with geometric series. If you haven't done that in a while, it makes sense. I'm not going to go through all the details so that you can refresh your own memory about it, because it's something we may see again. But just a hint, geometric series. So I think that actually answered the questions that I saw posted on the discussion board. Are there any other questions that anybody here has?
I have one.
Great.
So to go back to 1.16.
Yep.
On part C, it's more of a conceptual question.
Okay.
But you have probability of A not occurring or B not occurring.
Right.
Correct. So how does that convert to being 1 minus the probability of neither, or of A?
Okay, so let's look at a Venn diagram. Sometimes that.
Yeah, that's.
Okay, so let's see. So let's look at A and B. Okay, so let's see. We've got the union of A not occurring and B not occurring. So A not occurring is everything I'm shading this way. B not occurring. Wait a second. This is also A not occurring. Sorry. Right. That's A not occurring. Okay. B not occurring. Is everything there. Okay. When I look at the union, I'm looking for everything that's shaded in either way, right? Either A didn't occur or B didn't occur. So the only thing that's not shaded, you can see, is this intersection, A intersect B, is the only thing that was not in either A complement or B complement. Remember that when we talk about union, it's, everything that's not in A or not in B, or both. Right? So the only things that are not in A we've got everything here is either not in A or not in B, or both, except this intersection. So this is the only part that is known.
Okay. So when looking at the Venn diagrams in the book, the union of A or B is just the Venn diagram part of the Venn diagram, with the surrounding area being the other.
So we talk about, right, when we talk about A or B, right? A union B would be this part, right?
So it is not equal to being just
Right.
not A union B.
Right. Yep, it's actually equal to not being in the intersection of A and B,
Okay.
as opposed to not being in the union.
Okay.
Yep. I do think that the Venn diagrams sometimes are really helpful to kind of visualize some of these laws, kind of like, okay, figure out where we're at and think about what these events really are, because sometimes it's hard to visualize otherwise. Some people are really good at visualizing it, and some people are not so good at it, and some people develop a good sense for what these sort of intersections and unions look like over time. But most people, when they first start off, it's really helpful to try to sketch out the diagrams so they can get just a better sense of how the complements and the unions and things relate to each other.
If you had separate probabilities, would that change anything? If you had the probability of not A, and then the union of that with the probability of not B, is that different? Because I mean, looking at the Venn diagram seems not helpful, honestly, in this case. Because if you're considering the fact that it is neither of these,
Right.
and you look at the part that isn't highlighted,
Right.
that's not right.
So if I look
In
at the
the
part
book.
that's not highlighted.
No, in the book. Because if you look at the union of A and B, and then you look at what isn't highlighted, that isn't the correct answer. It's,
So if I look at the union of A and B.
right.
Okay.
So I'm just thinking of it as that being not the union of A, or the union of not
Okay,
A
so
or
let's think about, so what's not in A union B, right,
B. Right.
is, if you look at it, remember when we were finding that, we shaded what was not in A
Right.
and what was not in B.
Right.
So where I have crosshatches, right, where the intersection of those
Right.
is everything that's not in A union B. Right, so if you think about it this way. The part that's not in A and not in B is here, right? Not in A and not in B. And that's the complement of A union B.
Right. Okay, yeah. I guess the thing that's confusing me is the parentheses, assuming you would have to fill everything within the parentheses before. But I see what I get it.
Right. Like I say, it takes, I think that sometimes looking at these, really sort of shading them yourself, and because sometimes when you try to look at the ones in the book that are already shaded, it's a little bit harder to kind of wrap your head around. If you go through it yourself and draw them and say, okay, what's not in A, what's not in B, sometimes it's really, it just makes it all suddenly make sense. Any other questions that I can help you guys with today?
I've been working through 118. I started working through that. My instinct is that to figure it out, I have to use De Morgan's laws. Would I be on the right track there?
Okay, let me just peek at that one.
It has to do with.
Okay, so visiting a primary care physician's office, the probability of having neither lab work nor a referral to a specialist is 0.21. Okay, so the way I would start this is I would start by saying, okay, I've got lab work and I've got a referral. So I start by saying, okay, what is it telling me? The first thing it's telling me is the probability of having neither. So that means not lab work and not a referral, right? The probability of that is 0.21. Let's see, of those coming to the office, the probability of having lab work is 0.41. And the probability of a referral is 0.53. We want to know the probability of having both lab work and a referral. Okay. So this one kind of comes back to when I was talking before about finding probabilities of intersections, right? One of the ways we have to do it is by taking the probability of the lab work plus the probability of the referral and subtracting off the probability of the union of those two. Right? Just rearranging. We usually write this the other way. We say the probability of the union is the sum of the two probabilities minus the intersection, but it can be written this way too, right? So, okay, we know lab work and we know the referral, right? So we've got these two. What's the probability of having lab work or a referral? You're right, you need De Morgan's law, right? Because this part tells me that the probability of having lab work or a referral, because it's the complement of this event, is going to be 1 minus the probability of having lab work, not having lab work, and not having a referral. So now I can take 1 minus my 0.21. That gives me 0.79. And now I can use this to subtract. Is that kind of the approach you were on?
Yeah, and that I realized I actually made a mistake when I was, realized I made a mistake when I was talking about the problem into my notebook, so that also helps.
Okay,
there too.
good. All right. Anything else I can help you guys with today? Okay, so the next module, Module 3, is going to focus on Section 1.2, which is all about counting. We all probably learned to count before we went to school, so it all sounds very easy. Counting is challenging in this section. So if you start to get a little confused or frustrated, I encourage you to keep working at it, ask some questions and keep working at it, because we're going to be working with combinations and permutations, and the only way that you get good at it is by practicing with it. It's hard at first for most people. So don't get discouraged. Keep working at it. Use the discussion board to ask some questions and bounce ideas off each other. I'll go in there and check out the questions that show up and try to give some feedback too. But the best thing to do if you're having trouble with this section is to just practice, because that is how you get better at it. Okay, so thanks for coming, those who came, and have a good week.